to thanks for inviting me to give this talk. So yeah, today's talk will be return of a nanolab. So I have this idea that now with the new focused ion beam microscopes and PFIBs and also MEMS hot stages, now we really do have a sort of nano lab, which was what was envisaged in like the early 2000s when people were getting the first round of dual beam systems. So yeah, I'd like to thank my collaborators really at the start. There's a few different projects we'll present in this one, so yeah, just thanks to all of them. So essentially we'll just go through like an introduction to focused ion beam systems, and then some of the expectations versus reality of using a gallium fib versus a xenon fib. And then we'll look at the solutions that we might have to use if we're going to switch from gallium to xenon. And then we'll look through some in situ testing. This is like a sort of opening my lab book and just seeing what we've been working on in the last couple of years with in situ testing. So let's get started. So as Dan said, I work at the Loughborough Materials Characterization Centre. So we're in Loughborough, which is just in the middle of the country. And we do all the sort of things that Plymouth do. We're quite a similar centre. We offer consultancy, nano labs and short courses, as well as supporting PhDs and undergraduate training and study. So we've got a little team of us, and I'm fortunate enough to look after our Helios G4 PFIB, which is around 3 or 4 years old now. So it's a xenon plasma fib system equipped with a multi-species, multi-chem, which has got platinum, tungsten and carbon, and we have a symmetry EBSD detector and a large area EDS detector, all Oxford Instrument stuff. So it's a really nice system. We're very lucky to have it. So if after this you'd like to sort of use the system or collaborate in some way, feel free to get in touch. So just the basic operating principle of a fib. So essentially, or a dual beam system, essentially what we have is 2 columns. So we have an electron column and an ion column. With the electron column, we're able to do our imaging and analytical work. So we can do EDS, EBSD and imaging. And with the ion column, we're able to do imaging and also mill materials and deposit materials. And what's interesting is that we have the 2 beams at an angle to each other, typically in this case 52 degrees, with a stage that tilts eucentric to both beams. So we can tilt the stage and get ourselves normal to the electron beam or normal to the ion beam. And so this allows us to cut an area and then image the same area. And it also gives us a form of depth perception. So by having 2 beams, suddenly we can kind of see the height of a manipulator from the surface, and we can start to then micro manipulate things in a much easier fashion than if we just had 1 beam. So I like to think of it that it's like having 1 or 2 eyes. So you can suddenly you get depth perception when you have both eyes open. And if you like this, you can extend this metaphor a little bit further. Once we have gas injection systems and microprobes, it's like having hands. So we can cut things, we can pick things up, and we can glue things as well. So how does this ion milling system sort of work? So essentially what we have is a billiard ball model, if you like, where we have an ion that's accelerated at the surface and that hits the surface and sputters material away. And you can think of this as billiard balls, or we sometimes say like atomic jet washing. So if you were jet washing your driveway, sometimes you clean the driveway and then you get some material or some dirt hitting your windows. And we would call that a redeposition. So the ions hit the surface, they sputter some material away, and some material will be redeposited on the surface. We can also have some ions that remain inside the surface, so they're implanted, and this can result in residual stress. And the action of hitting the surface with the ions also causes sample heating. And along with this, we also get emitted electrons, so we can start to form images. So what controls do we have over the ion beam? So it's actually quite similar to an electron beam in that our accelerating voltage essentially controls the depth that the ions penetrate into the surface. and the current controls the number of ions hitting the surface for a given time. And so this allows us to change how quickly we cut something and also how accurately. So as we increase our current, here you can see a little example of a cross section of some lines that we've cut. So at low current, we have quite a nice sharp probe shape. And as the current is increased up to, this is 60 nanoamps, so high current, the probe shape isn't as sharp anymore, but we can make a much larger cut in a much shorter period of time. So by controlling the current, we can control how quickly we cut an area. So if we want to cut a very large area, we would use a very large current. And if we need a small, accurate cut, we'd use a very low current. And we can combine this with dwell time and how many times we raster over a surface to control the depth of a cut in a material. And we can start combining these different cutting functions to produce different shapes. So we can do things like staircase cuts where we try and minimize redeposition and make a nice clean edge, and also like cleaning cross sections where we'd raster the beam across and bring it closer and closer to the surface, again to sort of polish a surface, or just box cuts. And we can take this further, in fact, and start doing lithography and mill out all sorts of interesting patterns, maybe if we want to make microfluidic devices and things like that. So our next trick or tool that we have is to be able to flow precursor gases into the chamber. And these precursor gases can be broken down by the ion beam or the electron beam and essentially deposit a metal on the surface. And this is particularly useful for protecting samples. So if we want to prepare a TEM sample, we would protect the area with platinum or tungsten. And we can also use this for welding onto probes. So we can use this as a way of picking things up and moving them around. Some of the gases that we flow into the chamber can also be used to act as an etchant. So we can increase the sputter yield of materials by flowing a gas across the surface. So here's an example of how we might do a TEM lift out. So first we deposit some electron beam platinum, and then we deposit some ion beam platinum or tungsten in this case. So you can see the GIS needle in the top right corner, and then you can see we would do a staircase cut to make a lamella that is still attached to the bulk. So this is cutting at high current either side. And then we would tilt the sample slightly, and we would use a lower current to polish the surface. And then once we've done that on both sides, we could drop back down to 0 degrees and undercut the sample. So it's just held on by a little edge. And then we could bring in one of these probes I was discussing, and we could pick up this TEM lamella. So here we are bringing in the probe, welding it on with some platinum or tungsten, and then we would cut the edge of the sample off and lift it out of the bulk. So once we'd lifted out of the bulk, we could put it on a copper half grid. This is a copper half grid, and we just place it on the grid and weld it onto the grid, and then we could polish it down until it was electron transparent and use it for TEM. Second. So we won't show the polishing, it's a little bit long-winded. So what would that look like? So if we polished a sample down like an aluminium sample, we'd polish it so it was atomically, well, not atomically thin, it's like a 60 nanometers thickness, and then we could do some high resolution imaging on it, for instance, and see all the way down to the atomic level. So what's the applications of FIB? So TEM sample preparation is probably one of the key uses that FIB has. And I like to think of this as suddenly we have like a polishing lab inside the chamber. FIB cross sections are another really useful application of FIB, where we want to mill dissimilar materials of different hardnesses. This is especially useful, or very soft materials like tin, where they're very hard to polish manually, but with an ion beam, suddenly they're quite easy to polish. Ion beam imaging. Ion beam imaging generally gives you very good channeling contrast. So if you want to identify grain boundaries, but you don't want to do EBSD, it's not required, then this is a good way to go. We can do 3D reconstructions, and these are essentially like an extension of a FIB cross section, where we keep taking cross sections and images of a location and then reconstruct a 3D model of the material. And then the sort of part we'll be talking about today, which is in situ analysis, where we can do bending or heating of materials, depending on what tools we have in the chamber. And finally, atom probe preparation. I'd say these are the sort of main applications of FIB. So I wanted to talk about the change that's been going on really in the last couple of years. And this is the introduction of xenon ion beam microscopy from gallium ion beam microscopy, which has been the sort of traditional source of choice. So I think a good place to start really is looking at this question. What is the statistical significance? Sorry. So here we have a gallium fib cross section of some aluminium oxide platelets in rubber, and this was trying to recreate a NARCA structure. We wanted to know what the dispersion and orientation was and what sort of defects were there. And you can see with the fib cross section that we take in a sort of sensible time period, maybe an hour or so, we can only see an area of 80 platelets. So we don't really have any statistical significance from this. It's a nice data set, but it's not hugely useful if we want to do some more analysis, some deeper analysis. And this is where having a current source or a fib source where we can go to higher currents comes in handy. If we can go to a higher current, we can cut a larger area cross section in a similar time period. And suddenly we have a more statistical data set. So we go from looking at 80 platelets up to looking at 400 platelets. And suddenly we're starting to be able to identify a more statistical trend of what's going on. So we might see at the surface, there's a certain type of structure, and then further into the bulk, we get something a bit different, more uniformity, for instance. And this really led to this question of, can we get to deeper features and can we get more statistical significance? Has led people really towards xenon plasma fibs. So gallium sources are currently limited up to around 100 nanoamps, at which point the source size becomes very large. So that instead of milling a nice neat cross section, we mill quite a big hole. It's not very tidy. Whereas with the xenon sources, we're able to cut a much higher currents, all the way up to 2.5 microamps, with a relatively small spot size. What we do pay for with this, with the xenon fib, is that at low currents, we don't have as small a spot size as we would with a gallium ion beam system. So there are some other advantages to moving towards xenon. Gallium isn't necessarily compatible with materials like aluminium. So if we wanted to do TEM sample preparation with aluminium, we'd often find that you can form gallium-based precipitates inside the TEM sample. And so you start to see things that aren't really representative of your material of interest. And xenon eliminates these issues. You don't have the same segregation issues in materials like aluminium. So yeah, what were these challenges with gallium? So there was a limit on the coherence of the sources due to the current limit. And this limits the cross-section width that you can make and limits the sort of statistical significance of some of your results. There was also material compatibility issues, as we've discussed. So things like aluminium, copper, austenitic stainless steel, tin, and gallium containing materials don't always work the best with gallium. And then maybe there are some replacement issues. So over time, you need to replace your gallium ion source every year and a bit or every 2 years. Whereas with xenon, you just have a gas bottle that should last a much longer time period, maybe up to 10 years. And then if we're being slightly cynical, often for funding, universities needed the next thing. So lots of people have got gallium fibs essentially because you can only get funding for something new if we're cynical. So how did this all develop? It started off really with single gallium beam systems, and this is why it's so exciting. We've moved from, or so exciting now, we've moved from single beam systems. We've now got dual beam systems in a lot of universities in the country. Around the early 2000s, these systems started arriving. And then for material science, really got plasma fibs in around 2010 to 2017. And we also started getting laser fibs, which instead of using a plasma fib to cut a larger area, they use a femtosecond laser. And then people have also started iterating on this, where they've started adding in argon ion beams and broad beam mills onto their SEMs. So there's been a whole explosion since the late 2000s, around 2010, of different variants of fib, even moving towards multi-species fibs. So we can now implant with or mill with oxygen, nitrogen, xenon, and argon, and even combine femtosecond lasers with multi-species fibs. So it's a really exciting time to be working on focused ion beam systems. And things aren't just happening in material science, they're happening in biological sciences as well, where we've got cryofibs coming online, including cryofibs with multi-species and even with fluorescent microscopes underneath the fib. So you have a fib on top and a fluorescence microscope underneath. So you can do essentially having like an optical lab and a prep lab all in one system. But like all of these sort of new things, there's an expectation versus the reality. So this is what we expected. We expected to be able to cut really nice, large cross sections where we can see nanoscale features and macro scale features. So we can start to look at things like this large scale porosity, while also being able to look at the nanoscale precipitates. But what actually happens in some materials is that we get a lot of defects when we're cutting. So one of the main defects that we see is curtaining, where we get ripples running down the surface of the material. And this is something that we see a lot more with xenon ion beam systems than we do with gallium systems. And this is something that we've had to try and sort of overcome. And for materials like diamond, graphite, silicon carbide, and aluminium nitride, we've seen things like waterfall effects, where you get this like giant's causeway forming on the front of your sample. Like these sort of steps. So there've been a range of things that we've had to sort of come up with to try and mitigate these issues, and I'll touch on the different ways you can do it and some of a little more detail. So the first and probably the most important thing we can do is select the right platinum, carbon, or tungsten deposit thickness and hardness on top of the sample. And this is something traditionally with gallium you don't have to worry about so much. You can just deposit a fine layer, a relatively fine layer of platinum and make a cross section. But with the PFibs, you have to think about what voltage or what carbon percentage you use for that platinum capping layer. People also come up with rocking milling. So essentially we twist the sample as we polish, and that tries to get rid of some of that curtaining effects. Something we've been exploring at Loughborough is using xenon difluoride assisted polishing and silicon masks to limit the waterfall effect, and also low KV cutting. So I thought we'd touch on the xenon difluoride polishing. So here's an example of a zirconium sample that was cut. We took around 30 minutes to make 100 micron width cross section. And you can see it's got horrible curtaining on this side. And the EBSD looks pretty poor. You've got lines running through it, and also the grains have got like sawtooth edges where you've got these curtaining effects. However, by using that GIS needle, we can flow xenon difluoride into the chamber, and this increases the ability, the sputter yield of the material, and allows us to cut at high currents without getting curtaining effects. And so you can see for a comparable period of time, so around 30 minutes, we can get a significantly larger, so up to 520 microns width and 250 microns deep area cut. And as I was sort of saying before about statistical significance, with tricks like this, we can go from something that isn't really statistically relevant, we've just got 5 grains, to something that is more statistically relevant, so an area with around 300 grains. So something we can do some analysis on. So another thing we've been working on to try and overcome this waterfall effect in materials like diamond has been using silicon hard masks. So this is a trick really stolen from broad beam ion milling, where you place a large chunk of silicon on top of the surface of your sample, and this tidies up the shape of the ion beam and allows you to cut a much cleaner cross section. So here on this little video, you can see the silicon mask. And as we cut through the silicon mask, the cross section of the diamond improves. And we go from this image in the top right, where we've just got this horrible waterfall effect, to again, like a more usable image where we can see the different phases within the graphite. We can see the graphite, sorry, not graphite, diamond. We can see the diamond particles and also the cobalt binder phase. So just to sort of summarize, so gallium is still fantastic for TEM lift outs and small cross sections. We're finding xenon is slightly more challenging to make lift outs, although once you get your lift out done and polished, you can have a very small amorphous zone on there for TEM analysis. For cross sections, again, sometimes for very small cross sections, gallium might be more efficient. And if you want to do ion beam imaging, gallium is still much better than xenon, as you get much more contrast and much more channeling in gallium than you do with xenon. But if you need those very large area cross sections to try and gather some statistical significance, the xenon ion beam is fantastic. But you might need to work on how you perform that experiment. So you might need to play around with different settings before you get a perfect cross section with no streaking. Okay, so I thought for this part of the talk, we'll move on to the MEMS in situ heating and biasing. So at Loughborough, we're lucky enough to have the FEI MEMS hot stage or hot stage and biasing stage. It's essentially a silicon chip with a heating membrane inside and then copper biasing lines which run towards the center. So you can see right in the very center here, you've got like a heating zone with some little TEM holes where you'd place samples. And what's cool about this system is that you can operate it in the fib and you can also operate it in the TEM. So you can do like a multimodal sort of experiments where you do it in both systems, which is quite cool. So not just the FEI chips, but pretty much all the chips on the market use a similar technology of a silicon substrate with these silicon nitride heaters, and they all have essentially the same advantages in that they can be heated from around 40 degrees C up to around 1,200 degrees C with millisecond response times, so that they can heat very, very quickly. And they have a relatively low thermal mass. And this means that they have typically less drift, they give out less infrared radiation, and so they can achieve high heating rates while also allowing you to perform EBSD and EDS in situ. So with crucible holders, at a certain point you have a lot of infrared radiation and you can't do EBSD and EDS anymore, depending on your temperature. One of the issues with these MEMS hot stages is that they, or one of the concerns people often have, is that they are pre-calibrated using infrared thermal measurement inside the factory. So you're just given a correction value, and then you're measuring the resistance across this chip to determine temperature. So you're not physically measuring the actual temperature with a thermocouple, you're inferring it based on a measurement done at the factory. And this can lead to some concern sometimes by reviewers. They're not always sure that they believe those values and that kind of thing. Yeah. So we'll start just looking at what we've done so far. So we started out doing some in situ melting, and we'll go through that because it's quite a fun example. And then we've also done thermal aging and flash sintering, which we'll talk about in a bit. We've also tried doing coefficient of thermal expansion measurements. I'll just briefly touch on that. So for composite materials, you can't necessarily measure CTE manually because the sample size is so small. So what you can do is prepare a fib lamella and essentially heat it up and look at its change in length dependent on temperature. And that's been quite a fun little area of interest. So let's talk about this in situ melting. So this was essentially just our first test, trying out the hot stage to see what it was like. And we thought we could just have a try, essentially. We'd done some TEM in situ work previously, and we wanted to find out what it'd be like using the fib version. So we essentially took a SAC solder, tin silver copper solder bump, lifted out a little sample from the center of one of the solder balls using a standard lift out procedure. So we just gold palladium coated the sample, put some platinum down, and then performed a normal TEM lift out. And then we place this on the hot stage. So you can just see down in the bottom right corner, the little sample over one of the transparent windows. So we made quite an unusual shape in a way. We made like a sort of dog bone shape. And the idea was that we would be able to compare bulk, so thick parts of a sample, to thin parts of a sample, and see how those two areas reacted differently to the temperature applied. We also thought that maybe the thick sample might be better for EDS analysis, whereas the thin sample obviously would be better for TEM analysis. So we'll move on. So here's our first attempt at heating the sample. So you can see the red circle is what we would be able to see if we were in the TEM, but in this case we were in the FIB. And we're just heating the sample nice and slowly at 1 degree a minute, from 40 degrees to 100 degrees. And then once we get to 100 degrees, we're heating much slower at 0.15 degrees per minute. What we can see has happened is initially, I'll start it again. Yeah, we'll go through it this way. So initially you start to see the precipitates moving in the bottom left-hand corner. So they're starting to form together and produce new precipitates together. And then on the top edge, we can start to see diffusion from the tin into the platinum layer, and also tin nodules forming. So there are a few things we sort of initially learned from this. One, it's very difficult to decide when your sample is, in this case, like a tin sample, when your sample is molten or whether you're just seeing surface diffusion going on. The other thing was your surface coatings matter a lot. So this platinum layer was clearly reacting with the tin. And the other thing we noted was just having the limited field of view that we would have had in the TEM. So just having this red circle of field of view doesn't necessarily tell you the whole story of what's going on. The advantage of having this larger area is we can see more context. So if we were just looking in the TEM, we may not have seen these tin nodules forming. Just move on. So we could do a little bit of EDS on this, and we identified that these nodules, as I said, were tin-based, and this is like a similar process to, I think, like the research Dan does on tin whiskers. So we're essentially watching tin whiskers form from the platinum tin interface. It also shows, as we have a thicker sides, this is much better for EDS. It's far easier to pick out our silver precipitates. Whereas obviously where we have the thin sample, we have lower counts, so it's more difficult to identify the elemental composition, although we get better spatial resolution. Just to sort of demonstrate that point of what it would be like looking in the TEM versus looking in the SEM, this was a view from inside the TEM. You can see that our field of view is much reduced. And with that, we lose a lot of context as to what else could be going on in the experiment. So once we looked enough of the sample, we just had a bit of fun. So just to see what could be done. So we tried doing some thermal cycles on the tin. So here you can see we melted the sample. And what's interesting is the sample's actually got an oxide layer around the outside. You can just see like a halo of it here in the middle of the sample. And that seems to be holding the tin as it's molten. A few other people have commented on this, but this allows us to melt the tin, solidify it and remelt it again and again, and look at the different precipitates forming. So by changing the cooling and heating rate, we could form different precipitate shapes, which obviously was quite fun and gave us some ideas for future research that we could do. Yeah, I think this was just to show that the coatings that we use have a serious effect. So some of the precipitates formed, like the gold precipitates along this precipitate here, were from the surface coating on top of the sample. So we have to be quite careful. Well, I'll cover it here. So yeah, capping materials and coating layers before we perform in situ heating are really quite important. We need to make sure that none of those are going to interact with the sample of interest. So if we're looking at tin-based samples, for instance, we need to avoid gold, platinum, and silver coatings, as these can melt and form new precipitates inside the tin. And if we were looking at steels, for instance, if we carbon coated the steel before doing some in situ heat treatment, it's quite likely we would form new precipitates because we've got a carbon enrichment on the surface. So either we use capping layers which don't react with the sample, or we should remove the capping layer as much as possible before doing the experiment. We really found that SEM-based heating gave us a significantly larger field of view, which gives us a much more representative area to look at, and also made sure you could see like large-scale effects like those tin nodule growths that you wouldn't necessarily see before doing TEM. So our best practice in the center really now is to do SEM-based heating before TEM-based heating, if possible, as it allows you to iron out any of these sort of issues that you might come across but wouldn't see in the TEM. So next we'll look at how we continue this work doing some in situ heating of solders, so essentially thermal aging. So one of the research groups at Loughborough is doing self-propagating exothermic reaction bonding. So essentially they have like a little foil layer which you can ignite, it heats up and causes a solder to melt and solidify very, very quickly. And this allows you to bond samples like the one on the right hand side without forming any intermetallic compounds because the heating and cooling time is so quick. And this gives us a great opportunity to look at thermal aging and how those intermetallics grow from no intermetallics or very small intermetallics all the way up to fully formed intermetallics. And on this side is just like an example of what a normal solder joint would look like compared to a nanofoil bonded joint. So we took a sample from one of these self-propagating exothermic reaction or nanofoil bonded samples. We took a TEM lamella out of that, and you can see this is where the PFib really comes in handy. So the lamella size was 120 microns long, 50 microns deep, and 10 microns thick. So this was relatively easy to cut in the PFib, but if we've been using a gallium fib system, this would have taken a really, really long time and been quite challenging. But having access to those higher currents allows you to take these large bulk samples. So once we've taken that, we put it on the hot stage, and then we had a simple sort of experiment where we heated the sample up at half a degree a second up to 150 degrees, and this was our thermal aging temperature. And then we sort of cycled it up and down doing analysis once we'd cooled it down. And we did like a coarse sampling to start with and sparse sampling later on. So we did every 15 minutes doing EBSD scans for the first hour. And then for the subsequent time, we just did EBSD every 30 minutes. So this is one of the issues with these. It's relatively time-consuming process, but it's a better option sometimes than making an individual sample for each thermal aging condition. So here's a backscatter image set where we're heating up the sample and aging it. So you can see the time in the top left corner. And what we can see is intermetallics growing. We've got the copper at the top, the solder in the middle, and the nanofoil at the bottom, sorry. And as we heat the sample, we get intermetallics forming along that copper interface and also along the nanofoil interface. And interestingly, we can also see there's some layer starting to cover the copper sample. So if I get to start from the beginning again, you can see there's a layer forming across the copper. Okay. So looking at this with the EBSD, what we can do is track what phases are where within the joint, and also what their orientation is, what their size is, and what phase we have. So over time, you can see at the start, we just have a few silver precipitates and not really any intermetallics formed at the copper or nanofoil grain boundary. And then quite quickly, we start to form intermetallics at the grain boundaries and also start to grow intermetallics at both faces, sorry. Then over time in the bulk, we start to see some of the intermetallics joining and forming larger and larger grains. And at the copper face, we see the copper 6 tin 5 actually traveling across the surface and forming intermetallics across the copper, which was quite unexpected. You wouldn't necessarily expect to see this. Oh, whoops, sorry. Yeah, I'm not sure it's super. Okay, yeah, sorry, that won't work. So based on these results, we can track the intermetallic growth at each face, and we can start to comment on what mechanical properties we might expect from the joint. So from the copper face, we see, well, both faces have got a similar growth rate initially, and then the nanofoil face doesn't have as many IMCs grown, and it starts to slow down its growth rate, whereas the copper IMC layer seems to increase and then steady out later on. And we also start to see like coarsening of the precipitates as well later on during the thermal aging. So based on this, we'd expect a failure in the nanofoil rather than the copper interface, as the nanofoils formed a much thinner layer of intermetallics. And yeah, I think that's probably as much as we go into on this one. So next, I thought we'd talk about flash sintering, just sort of touch on that. So by applying, so for ceramics, if we'd like to sinter them, one of the ways we can sinter them at low temperature is by applying a current to them. So in a conventional sintering of something like zinc oxide, we would sinter it at 1,000 degrees, sorry, 1,200 degrees, maybe for an hour or so. Whereas with flash sintering, we can just take the furnace up to 400 or 600 degrees, apply a current, and cause what's called a flash to occur. And in that case, the sample will sinter just within a few minutes without having to go to that really high temperature. This is quite, well, super exciting really for ceramicists, as it allows you to sinter samples at lower temperatures much quicker, and it can sometimes, sometimes it results in a smaller final grain size. So what we wanted to do was do this in situ. So here we have in situ stage with the biasing setup. So we've built like a little holder for that. And what we can do is make a ceramic sample. So this is a zinc oxide sample that we've placed onto the hot stage. And then we've drawn biasing lines with our tungsten deposition. So we can heat the sample up and also apply a current and a voltage to the sample to cause it to sinter. So in this case, we had, as I said, zinc oxide, which we're going to heat to 600 degrees and then apply a current and voltage to it of around 1 to 2 volts and around 250 millivolts. So this is what the sample looks like just being heated up to 600 degrees. So you can see there's not a lot of change. Not much has happened. Maybe just the cracks have changed slightly. And then if we take the sample here, what we're going to do is apply the voltage, and you can see that as the voltage is applied, the whole sample sort of comes together. Some cracks start to form. We lose this top edge over the top left-hand side, and the sample's actually shrunk. And as it's shrinking, it's starting to pull away from the tungsten deposits. And this is a sample being flash sintered in situ. So the plan is to be able to observe this as it happens, and we're sort of working towards that. So you can see pre-sintering, sample sintering at 600 degrees, initial flash sintering, and then the completed flash sintering, where the tungsten biasing lines are broken, so we've had to stop the experiment. So did we actually manage to flash sinter the material? So one way of checking this is to look at EBSD mapping and see if we've increased the grain size and how indexable the grains are, like how crystalline the material is. So we started off with the unsintered sample on the left here. And after flash sintering, we suddenly have, you can see a lot more grains are indexable, and also the grain size is increased. From this on the left-hand side, you see much more larger grains across the sample. And just like a little zoom in on an area. So here you can see, again, like the grain size is significantly increased. And there might be like a grain boundary phase that's formed. So that's really my talk for today. Hopefully shared with you a little bit about how dual beam systems work, all the exciting stuff that's going on with all the new xenon fibs and also multi-species fibs, and then shown some of the MEMS in situ hot stage work that's been going on with Loughborough, and sort of touched upon some of the things that you might want to think about if you're going to do in situ heating. So concerns about whether you have the right surface coatings and how bulk versus surface effects might change your results. So thank you very much for your time. If you have any questions or comments, that would be great. And if you'd like to follow me on Twitter, I post quite a few of my experiments. So sometimes it's interesting. I always like to talk about microscopy on there. So thank you very much.
Thank you, Stuart. That was really cool stuff you're doing down there. I really like those in situ tests that you're doing. The melts that look really interesting. You can see the diffusion of the tin going around, and it looks really cool. And then you got your intermetallics forming on your solders.
Yeah, it's a lot of the stuff similar to the work you were doing before, where you, it turns out you can form tin whiskers in situ, which is quite interesting. Yeah.
I did find that a little bit annoying with some of my samples. If I were to fib it and then didn't have enough time to really do the rest of it overnight, I'll then find out that there's a whisker going on my cross section. I was like, okay, now I've got to prepare that again.
Yeah, time to do it again. Yeah, we've noticed that with the xenon fib, because you can go to so much higher currents, you can actually recrystallize the tin. Cool. So you can completely change your microstructure if you go too crazy. So yeah, a double-edged sword.
It's interesting that you saw that there was a fusion going both ways, or somewhat. You got your tin going into your copper going into your tin. I saw that on my samples. So obviously I got electroplate on either copper or brass, but I've got the copper going into the tin, but I've got the tin going into the substrate and forming intermetallic compounds as well.
Yeah, so I have an inkling that because you're milling the cross sections in situ, you're not forming any oxide layer, or you're forming a very thin oxide layer. And because you're keeping the sample in vacuum, under vacuum the whole time, you've got like a fresh copper surface without an oxide. So suddenly the tin can transfer across there. Whereas normally, if you just vented the chamber, you'd form a really thin oxide, and then you wouldn't see that migration in the same way. So this is where we sort of worry. Sometimes it's not really representative. And you have to be quite careful whether what you're seeing is real or not. Obviously, if you did that in as a TEM experiment, you probably wouldn't have a vacuum transfer. So you would have inadvertently formed a very thin oxide, and then you'd be, oh, I don't see that in my sample.
Of course, yeah.
It's been interesting.
It's nice, though. Those are really nice experiments that you're doing. I like that flash sintering as well.
Yeah, thanks. That's
cool.
taken some work.
Was that EBSD, just normal EBSD, or was that TKD on that lamella?
It was normal EBSD, which is pushing the limits of.
I'm going to say those grains are quite small.
Yes, that was a 25 nanometer step size in zinc oxide, which is probably about as far as you can take it. I think if you wanted better results, you'd be better doing TKD.
Yeah, that's usually, when I'm doing like 3D EBSD on my tin samples, it's usually that 25 nanometer that I'm usually going to, just because those tin metallics can be so small.
Yeah, definitely. And thankfully, like with the symmetry, you can just drop the voltage down a little bit, and then you can get down to 25 kV. Sorry, to 25 nanoamps. Yeah, I'm not sure I believe it at 20 kV in zinc oxide. It's probably not going to work well.
Cool. Okay, so if anyone's got any questions, just raise your hand, or I think Hong's got a question.
Yeah, first of all, I want to say Happy New Year to everyone, and it's nice to see you on this occasion. And I have been, studied in lab materials for 4 years during my PhD, and also visited Plymouth, a couple of times, and was very nice seeing your team there as well. So I want to say hello, and also thank you for organizing this. I found the presentation is really good, and with lots of information. I felt that there was a pressure on me to learn something new. And I was thinking 10 years ago, actually more than nearly 20 years ago, I used the Nano lab in the lab, and I still have another Nano lab in my lab. And I just felt like, the technology has been, advanced so much. So there is an intention for me to catch up. But given the busy daily schedule, I will see what I can do. But I want to ask a general question for Stuart, because it's lots of accessories on your machine, and lots of very sensitive parameters and stuff. So I wonder, just from your daily, roles, do you investigate these parameters yourself, or you let students to investigate? Because I give student training, but they are quite standard procedures, not so complex.
Oh, thanks for the question. I'm really glad you enjoyed the talk. If you ever want to visit Loughborough, you're more than welcome. Yeah, for sure. It really depends on the project. Typically, we just optimize the settings with the student, sat on the microscope together. And then if they want to, as they learn, as they want to, improve the process, we could work on it a little bit more together. It just depends on how long they're going to spend on the system and how much time they've got available. You probably find the same. Some students, you're going to do maybe 40 samples or something, and in that case, it's worthwhile them working on what they really want. But otherwise, we're similar. We would just give them quite a standard set procedure, and that's been a little bit of a challenge, with the PFIB, because sometimes the standard set procedure isn't always perfect. It's not always that simple. Whereas with the Nova, like we found, the lift out procedure is a lift out procedure. It's the same every time, and it works every time.
Yeah, makes sense. And do you open to like external people? Yeah,
certainly. So as an external academic, you're more than welcome to get in contact, and we can run the system for you, or you could get trained on the system as well. And come and visit.
When I look at your images, I felt relieved, good, because you showed a cross section of hundreds micron thickness cross section. It's just coincidence that recently I was sent a sample and the student said to me to measure thickness, and when I look at it, when I was preparing to look at it, I thought this is very thick, and then I just do the general routine mechanical cross section, not on the FIB, and it turned out to be 400 micron thickness. I could be sitting there days of thinking to get it through. So it's useful for me, especially first time seeing the capacity of PFIB. So thank you.
Oh yeah, pleasure. I think it's sometimes the manufacturers sell it as being able to do these 400 micron really easy as well. But from experience, sometimes it works well. Sometimes it's very material dependent.
Very delicate facilities to get the best result. Yes, I understand. Thank you, and thank you Dan as well.
Cheers, Hong. I got a quick question that some people might have thought about. Why would you deposit electron beam platinum first before putting an ion beam platinum?
So just the electron beam platinum doesn't damage the surface in the same way. So as the ion beam comes down when you're depositing platinum, it's partly depositing and partly milling as well the surface, potentially, depending on how well you've balanced the amount of gas coming in versus the current you're using. So if you really don't want any ion beam damage on the top surface, it's best to protect your area of interest with electron beam platinum first. It's depending on what you're doing, it's not completely necessary, but it really is best practice. And sometimes your TEM specialist might thank you. Sometimes they like a mix, they like to see two layers, but it depends.
Yeah, we do that. Sometimes you can see it really nicely, can't you? That really thin, brighter kind of layer.
Sometimes it's nice to have a thick carbon layer as well. Sometimes if you've got something similar to platinum. So if you're looking at, I don't know, some other heavy metal, sometimes a nice carbon layer can help you.
Yeah, you get a nice contrast then.
Then I'm not looking at my deposit.
Hey, Stuart. Sorry, feedback. It was great talk, thank you. Just a question. Sorry, I'll come over here. Sorry, that's terrible.
Right.
So with the we're back. With the let's say you're putting down unreduced platinum or something on a gallium FIB, you'll normally end up with a horrible mix of platinum and gallium and carbon together. And I was just wondering how the sort of purity or the contamination compared with the plasma FIBs. Do you end up with more of it being the platinum or tungsten you're trying, or?
It's a bit funny with the plasma FIB. So we actually mix carbon in on purpose. to change the hardness of the deposit. So depending on what you're milling, you add in, well, you're a FIB guy, you probably know some. Yeah, we often add in carbon on purpose to increase the hardness, and you try and match the hardness of your platinum deposit to the sample that you're cutting. So if you have a hard sample, you add more carbon, as that's difficult to cut with the ion beam, and that increases the hardness of the deposit. With regards to actual like cleanliness, like if I deposit tungsten and I don't mean to have any carbon in there, I'm not sure what our cleanliness is like. I imagine it's just depends on how clean the chamber is at that time. Yeah, that's sort of as far as much as I know on that.
Cool, thank you. And with the in situ heating experiments, is there anything that has sort of particularly surprised you with how different the behaviour has been? So I've only ever done a little bit of sort of MEM stuff with a number of years ago with Giorgio, actually, who's in the audience, and we were looking at some little nano droplets of indium, and they disappeared, presumably sort of disintegration on the surface or diffused away a good few hundred degrees below their melting point, and was obviously under a very different sort of set of circumstances under the diffusion we're expecting under sort of a normal gaseous environment. Have you, how confident are you in the sort of experiments you're doing that they're representative of your?
Yeah, so we've seen things like that, and I think that's partly, as you say, partly due to the pressure and partly due to Kelvin evaporation, because rather than looking at a bulk, we're looking at really small particles, and so they're evaporating from a sharp edge rather than just being like a big block of material. So yeah, in that in situ heating of the tin, for instance, it probably would have evaporated if it didn't have the oxide layer. And some of the areas were potentially evaporating or at least moving at much lower temperatures than you would have expected. I think that might be to do with like thermal mass, or I'm not completely sure. But that's why we've moved more towards doing thick samples rather than the really thin TEM samples, because otherwise I don't really see how you're not doing something that's just surface dominated.
Yeah.
Also, just because your data is more easy to analyze. If you have EBSD, you've already got an idea of what's going on, what phases are what, rather than in the TEM sort of having to take EDS maps so frequently to try and work out what the contrast is. One surprising thing we've seen quite a bit of has been the amount of gallium that comes out of your samples when you heat up a sample. So sometimes, like if we're looking at graphite samples for CTE, we'll take the graphite fib lift out from the gallium fib because it cuts so much better than the P-fib for graphite. And then when you heat that sample up, you actually see the gallium coming to the surface and you see beads of gallium forming, which I still can't quite get my head around, because to see beads of gallium, that means that there's, a mass, quite a large mass, in fact, of gallium inside the sample, which is still quite surprising to me. Every time you're like, really, all of that? And also its reaction with platinum. So sometimes you get the two things sort of joining together, which makes it look even worse. But we found you can literally just evaporate that stuff off. So if you have a graphite sample, you can take it up to 800 degrees and just essentially boil off the gallium, and then you can start using your sample like normal without any gallium contamination inside it. And the same thing might be happening for xenon. Obviously, we can't see it. So.
With the contamination from your strap, do you see any improvement if you mill it from the backside? A lot of people mill their TM specimens upside down to avoid that contamination, or once it's hot, do you just get so much surface diffusion anyway that it doesn't?
So sometimes we just cut the platinum strap off completely, and that normally helps. So if we're doing CTE tests, you have to cut the platinum strap off. It's often the CTE difference between the sample and the platinum strap is so significant that you see like a whole sample bananas up like that, or well, one way or the other, because the platinum is expanding more than, for instance, the graphite. So if we really don't want that to have any effect on our experiment, we just cut that off and then repolish each face without a coating, without a capping layer, which is not ideal. You get a little bit of streaking, but at least you've not got that elemental contamination and residual stress. Yeah.
Brilliant, thank you. It's great talk.
Thanks. Thank you very much. Yeah. Great.